Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we will continue to discuss the motion of rigid body, part 2 from the paper Classical Mechanics. After studying this module, you should be able to understand and learn the use of three generalized coordinates in the form of Eulerian angles to describe the motion of a rigid body. You will further learn to describe the motion of a rigid body in the absence of any external force in terms of Euler's equations of motion. We have seen that a rigid body has 6 degrees of freedom. We thus require 6 independent generalized coordinates to specify its configuration. There may be additional constraints on the body which will further reduce the number of degrees of freedom and hence the number of generalized coordinates required to specify the orientation and position of the rigid body. These additional constraints would be in the form of the symmetry in the shape of the rigid body, etc. In order to describe the motion of the rigid body, we need to derive the equations of motion from the Lagrangians appropriate to the rigid body. How to assign these coordinates? This can be done by setting a coordinate system in an inertial frame, as will be explained just now. We fix the coordinates of a rigid body to begin with. So let us identify the body fixed coordinate system sigma prime with the prime coordinates x prime, y prime, z prime, and an inertial coordinate system sigma with the unprimed coordinates x, y, and z. Just refer to the figure. Then we make a translation motion of the inertial frame so that the origin of the two systems coincide, and we have shown the inertial axis now by dotted lines. There are several ways in which the Cartesian axis with a common origin can be specified. A straightforward way is through the direction cosines of the primed system with respect to the unprimed system. If we denote the unit vectors along the coordinate axis of the unprimed and the prime system by I, j, k and I prime, j prime, k prime respectively, then we can always express the prime coordinates in terms of the unprimed coordinates using the direction cosines. For example, we can write x prime as alpha 1x plus alpha 2y plus alpha 3z, where alpha 1 is the scalar product of I with I prime, alpha 2 j with I prime, and alpha 3 is the scalar product of k with I prime. Similarly, y prime can be written as beta 1x plus beta 2y plus beta 3z, where beta 1 is equal to the scalar product of the unit vectors I with the j prime, and likewise for beta 2 and beta 3. Similarly, the prime coordinates z, the z prime can be written as gamma 1 x plus gamma 2y plus gamma 3z, with gamma 1 given by the scalar product of the unit vector I with k prime, gamma 2 j with k prime, and gamma 3 k with k prime. Since the coordinate systems are Cartesian, we have the scalar product I prime dot I prime, j dot j, k dot k, etc. equal to 1, and I dot j is equal to I dot k is equal to j dot k is equal to 0, and similarly for the prime unit vectors. There are 9 possible products between the unit vectors in primed and unprimed systems. Rotation of the coordinate axis leave the magnitude of the radius vector of any point in the rigid body unaltered. We thus have 6 relations between the product of direction cosines, namely alpha j alpha k plus beta j beta k plus gamma j gamma k is equal to 0, for jk is equal to 1, 2, 3, and j not equal to k if j is equal to, and alpha k square plus beta k square plus gamma k square, all for k is equal to 1, 2, 3. We can thus use a set of 3 independent functions of direction cosines as generalized coordinates. Now, it turns out that a more convenient choice of three generalized coordinates for describing the motion of a rigid body is through what are known as Eulerian angles rather than these direction cosines. What are Eulerian angles? The most common and useful choice of the three generalized coordinates is to define the three Eulerian angles. A transformation from a given Cartesian system to another can be performed by three successive rotations through these angles in a specific sequence, which will take the inertial system xyz to a body fixed system x prime, y prime, z prime through a successive rotations. The transformation can be represented in terms of a matrix equation. The coordinates x, y, z are rotated by orthogonal matrix R to the coordinate x prime, y prime, z prime. We will define this rotational matrix R through a sequence of three rotations on x, y, z as follows. Number 1. The first rotation is by an angle phi about the z-axis. This results into the coordinate system labeled by xi, eta and zeta axis. The transformation from the xyz to xi, eta, zeta coordinates can be affected and can be written in the form of a matrix. Xi, eta, zeta is equal to a 3 by 3 matrix with the entries cosine phi, sin phi, 0, minus sin phi, cosine phi, 0, 0, 0, 1 acting on the coordinates x, y and z. The second rotation is counterclockwise through an angle theta about the xi axis, and this transforms the coordinates system from xi, eta, zeta to xi prime, eta prime, zeta prime through the rotation by an angle theta as again in the form of the similar equation as we have for the rotation by phi angle, and therefore we can write xi prime, eta prime, zeta prime is equal to a 3 by 3 matrix as shown in equation 19.8 acting on the vector xi, eta, zeta. The xi prime axis is at the intersection of the xy and xi prime, eta prime and is known as the line of nodes as shown in the figure. The first rotation is by phi, the second rotation is by an angle theta as shown in the diagram. The third rotation is now counterclockwise through an angle psi about the z prime axis, which results in the final coordinate system x prime, y prime, z prime. The three Euler angles completely specify the orientation of the two coordinate system. So the third rotation in the form of matrix is written in equation 19.9 as x prime, y prime, z prime obtained by the rotation by an angle psi and given in terms of the matrix in equation 19.9 and shown in the figure. Now we can collect the three rotations together, and therefore the matrix of complete transformation can be written as x prime, y prime, z prime is equal to a matrix which is a function of now the three rotational angles psi, theta, phi acting on the body fixed coordinates x, y, z, where the rotation matrix R psi, theta, phi is the product of the three rotation matrices by angle psi, theta and phi respectively, and it is given by this 3 by 3 matrix shown in the equation 9.11, whose diagonal elements, for example, are cosine psi, cosine phi minus cosine theta sin psi, minus sin psi sin phi plus cosine theta cosine psi phi and cosine theta. The other elements are shown in equation 911. Now the transformation from the inertial coordinate frame is given by the transpose of R. That is to obtain xyz in terms of the inertial coordinates x prime, y prime, z prime. We can obtain that by acting on the vector x prime, y prime, z prime by the transpose of this rotation matrix. rotational velocity about the body fixed axis. The body fixed axis turned out to be the most useful for the discussion of rigid body motion. In order to write down equations of motion for a rigid body, when Euler's angles have been used as generalized coordinates to fix the orientation of the body fixed axis, we would require to express the rotational velocities expressed as time derivatives of the Eulerian angles, and this is done as follows. We see from the above discussion, in particular from equations 19.7 to 19.11, that the angular velocity phi dot is along the inertial frame axis, theta dot is along the line of nodes, and psi dot is along the body fixed axis g prime. In terms of components, the phi dot has x and y component 0 and is along the z axis, theta dot has the x component and the y and z components are 0, and psi dot has only the z components, x and y components being 0. Thus, the components of the angular velocities phi dot, theta dot and psi dot along the body fixed coordinate axis as angular velocity omega components are given by the components of angular velocity omega are omega x prime, omega y prime, omega z prime. These are the components of the angular velocity in terms of the initial frame coordinates. So, omega x prime, y prime, z prime is equal to the rotation matrix, which is a product of three rotation matrices r psi, r theta, r phi, acting on the vector with the z component phi dot and x and y component being 0, plus a rotation product of rotation matrix r psi and r theta acting on a vector which has x component theta dot and the other two components 0, plus rotation matrix r psi acting on the vector with x and y component 0 and z component psi dot. Putting all this together, we obtain the components of the angular velocity omega in terms of the Euler angles theta, phi and psi as omega x prime is equal to phi dot sine theta sine psi plus theta dot cosine psi. Omega y prime is phi dot sine theta cosine psi minus theta dot sine phi. Omega z prime is equal to phi dot sine theta plus psi dot. This transformation or this expression of the angular velocity omega of the body in terms of the Eulerian angles theta, phi, psi is very important, and this is the result which we will be using subsequently. Let us now obtain the Euler's equations of motion for a rigid body. We will first consider the motion of a rigid body in the absence of any external force, that is free motion of a rigid body, which consists of translation and rotations. In this situation, there is no potential energy associated with the body, and the Lagrangian reduces to the kinetic energy term for the rigid body. We choose the body fixed axis along the principal axis of the body, in which the kinetic energy, as we have seen in the earlier units, can be written as T is equal to 1/2 sum over I of ith component of the moment of inertia into omega I square. Now we will choose the Eulerian angles phi, theta and psi as generalized coordinates, and we can then write down the Lagrangian equations for these coordinates. The Lagrangian equation for the coordinate psi, for example, is given by dt by d psi. There is a partial derivative of t with respect to psi is the total time derivative of the partial derivative of t with respect to psi dot. T is a function of omegas, which in terms are given in terms of generalized coordinates, which in our case we have taken to be Euler angles and velocities. We can thus express the equation of motion as sigma over I dt by d omega I by d psi minus d dt of sigma over I dt by d omega I by d psi dot is equal to 0, where we have called omega x prime, omega y prime, omega z prime as omega 1, omega 2, omega 3 respectively for simplicity. We get the equation by finding the partial derivatives of the omegas with respect to psi and psi dot. So we find from our earlier result, from the expression for omega in terms of the Eulerian angles and velocities, partial derivative of omega 1 with respect to psi is phi dot sine theta cosine psi minus theta dot sine psi, which is nothing but equal to omega t. Likewise, the partial derivative of omega 2 with respect to the Euler angle psi is equal to minus times omega 1, and the partial derivative of omega 3 with respect to the Eulerian angle psi is equal to 0. We thus obtain d omega 1 by d psi dot is equal to 0, d omega 2 by d psi dot is equal to 0, d omega 3 by d psi dot is equal to 1, and dt, the partial derivative of the kinetic energy with respect to omega 1, omega I is II, omega I. Therefore, the Lagrangian equation simply become I1 omega 1 omega 2 plus I2 omega 2 into minus omega 1 minus the time derivative of I3 omega 3 is equal to 0, which can be written as I1 minus I2 multiplied by omega 1 omega 2 minus I3 omega 3 dot is equal to 0. Now, the designation of any axis as the principal axis, which we can call any axis as 1, 2 or 3. This arbitrary, therefore by permutation, we can write the other equations as I2 minus I3 omega 2 omega 3 minus I1 omega 1 dot is equal to 0 and I3 minus I1 into omega 1 omega 3 minus I2 omega 2 dot is equal to 0. These three equations are called the Euler's equations for the case of force-free motion of a rigid body. Now, Euler's equation in a force field can be obtained because the torque acting on a particle in an inertial frame is defined as the total time derivative of the angular momentum in the inertial frame is equal to the torque. So, in terms of the body fixed axis, the total time derivative of angular momentum in the inertial frame is equal to the total time derivative of angular momentum in the body fixed frame plus omega cross L, as we have seen over and over again. The equation of motion is then given by the time derivative of the angular momentum in the body fixed axis plus omega cross L is equal to torque. The components along the z-axis in the body is, for example, L3 dot plus omega 1 L2 minus omega 2 I1 is equal to tau 3, where Li is equal to II into omega I, since the axes are chosen along the principal axis of the body. Therefore, the three equations of motion of a rigid body in the presence of external force become I3 omega 3 dot minus I1 minus I2 into omega 1 omega 2 is equal to tau 3, and by permutation for omega 2 dot and omega 1 dot as shown in the equation 19.27. Let us illustrate with the help of an example. We will consider dynamics of a rigid body by calculating the kinetic energy of a homogeneous cone. We will consider the case when the base of the cone rolls without slipping on a horizontal plane, when its apex is fixed at a height. So, apex is fixed at a height. This is the cone. Cone is rolling on a horizontal plane. As shown in the figure, the cone has a height h and its half angle is alpha, its mass is m, and its radius at the top is capital R. Let x, y, z be the coordinate system of the inertial frame and x prime, y prime, z prime be the coordinate system of the body fixed frame. The origin of the body fixed frame is chosen at the center of mass of the cone, which lies at a distance of 3/4 from the apex. So, if you look at the picture, you can see that this is a cone which is fixed along the z-axis and free to roll in the xy plane, and the body fixed axis and the inertial axis are shown you can see that the body fixed axis origin coincides with the center of mass of the cone. The z prime axis of the body fixed system is taken along one of the principal axes of the cone, passing through the apex and the center of mass. X prime axis is chosen perpendicular to the line ACM as shown in the figure, and y prime axis such that x prime, y prime, z prime forms a Cartesian system. Now the cone rolls with its base in the xy plane. The instantaneous axis of rotation is along the line AC, and the velocity of the center of mass v is equal to this length ACM into theta dot. The ACM is 3 by 4 h, so the velocity of the center of mass is 3 by 4 h theta dot. The angular velocity of the center mass about the axis AC is omega, which is v into the distance BCM, which is equal to v by 3 by 4 h sine alpha, which is equal to then theta dot by sine alpha. So v is equal to 3 by 4 h theta dot, and omega is theta dot by sine alpha. The angular velocity omega is directed along the axis AC. The components of omega along the body fixed axis are omega x is equal to 0, omega z is equal to omega cos alpha, omega y is equal to omega square minus omega x square minus omega z square under root half, which is omega sine alpha. We thus have angular velocity components omega simply given by the x component of omega is 0, the y component is theta dot, the z component is theta dot cotangent alpha. The kinetic energy, being the sum of the translation energy and rotational energy, is given by half mv square, where v is the velocity of translation, plus half sigma I omega I square. And when we put the expressions for omegas, we can express the energy T in terms of the angular velocity theta dot and the moment of inertia. In the previous unit, we had calculated the moment of inertia of a homogeneous cone about the principal axis, and we had obtained that I1 is equal to I2 is equal to 3 by 5 total mass times h square plus r square by 4, and the moment of inertia about the third principal axis was found to be 3 by 10 mr square. So substituting all this together, the kinetic energy of the rolling cone comes out to be 3 by 40 mh square into 6 plus tangent square alpha theta dot square. So students, let us summarize what we have learned in this module. We learned that 3 generalized coordinates required to fix the orientation of a rigid body are required, and we can use a set of 3 independent functions of direction cosines as generalized coordinates. But a very convenient choice of these 3 generalized coordinates is not in terms of the direction cosine, but through the Eulerian angles, which makes the description of the motion of a rigid body more convenient. The motion of a rigid body in the absence of any external force is described by a set of Euler's equation with the choice of axis along the principal axis of the body.